All right. So a buffer is defined as a solution of a weak conjugate acid-base pair. Now, what's pretty cool about this is if you have the two of them together, the conjugate acid and the base pair, and they're weak, they have the ability to combine with either H plus or OH minus. And we'll talk a lot about that. They are particularly resistant to pH changes even when strong acid or base is added. And they're really good at what they do. And like we said, our bodies have buffer systems in there. Because we can take in things that really should be a problem to our body chemistry, but we have a buffer system to take care of excess H plus or OH minus. Because even a little change could make a big difference. And I'll pause this. So here we go. The easiest buffer to talk about is if you have HF and F minus in your solution. Okay? So I have an acid and I have the conjugate base, and we know this is weak. We know HF is weak because I didn't memorize it as a strong, correct? Okay. So what happens when we put something in here? If I add NaOH, that's pretty much just adding OH, correct? All right, so we can ignore the Na because it's the cation of a strong base. So we put OH minus in here. And what OH minus is going to do, it's going to react with the H that's stuck to the HF. And it's going to form water. You okay with that? That makes more F minus. That will affect the pH a little bit, but not drastically. If we add just OH to water, we add that in there, the concentration of OH is just going to go straight up. But here, since some of this HF can dissociate, it will grab that OH and tie it to water. And so even though I added OH, I didn't add OH minus very much. Sure, I added a little, and the pH will change, but not very much. Now, let's come along and let's add a strong acid. If I add HCl in here, we don't really need to worry about Cl either, because it's the anion of a strong acid. So I'm adding H plus to this solution. H plus will come in here and do what immediately? It will grab HF, because the plus and the minus, and HF is a weak acid, right? So the amount of acid goes up, but if it's weak, it's stuck together. All right, so even though I increased the amount of H plus, well, it was all absorbed into HF, so the pH didn't change very much. Okay, so this buffer can accept OH minus and make water out of it. This buffer can accept H plus and make HF out of it. All right, hold on. Since both of these are weak electrolytes, they stick together. So even though we added these things, the concentration of H plus and the concentration of OH minus only changed a negligible percent. So the pH doesn't change very much. Yes? That's a weird way to ask that question. Most kids don't hate this, by the way. Like it's manageable. Okay, this is just saying what I just said. If a small amount of hydroxide is added to an equimolar solution of HF and NaF, for example, the HF reacts with OH minus to make F minus in water. If a small amount of hydroxide is added to an equimolar solution of HF and NaF, for example, the HF reacts with the OH minus to make F minus in water. I feel like that's the same sentence. Everybody, you are welcome for me reading to you twice. Why is it there twice? I thought I was going to talk about H plus.
Oh, golly, that was fun. I hope you enjoyed it. I know I did. Oh, hey. Yes, there will be an effect.
Like the pH will change. Yes, but really, really small. And we'll show you how small versus how big it should be coming up pretty soon. I wonder what this is going to say. Should I read this one twice for fun? Here we go. If acid is added, the F minus reacts to form HF. Okay? It can take both and attach them. It's like a party with extra boys or girls. You bring another boy in, he's going to find a girl to hang out with. Bring another girl in, she's going to find another boy to hang out with, and so forth. Okay? All right. Buffer calculations. The rest of the hour, we're just going to straight up do math. So consider the equilibrium constant expression for the dissociation of a generic acid, HA. Like we've written the same thing before. HA plus water goes to H plus A minus. So don't stress about this. Let me just talk. All right. If we take this and we do some math, just trust me here. We do some math. All right. If we take the negative log of both sides, we would get the following. The negative log of Ka equals the negative log of H3O plus the negative log of A minus over HA. It's not too much. Like, you should, and hopefully will, love this equation. Because if we don't do it this way, we have to do a complicated ice table every single time. Yes. Was that fun? Not really, right? Okay. So all we did is take the negative log of every single thing, and then we did math. Like we have multiplying here, which in log land can be plus. Are you okay with that? It is. Trust me. You haven't had logs yet. All right. So we've just rearranged it, and we come up with what is called the Henderson-Hasselbalch equation. So if we look, pKa equals pH minus the log of base divided by acid. Coming back real fast here, that's just the pH, right? The negative log of H plus, or H3O. Okay, so simplifying it, all right, the pH equals the negative log of Ka plus the log of A minus over HA if we rearrange it. This is the Henderson-Hasselbalch equation, which lovingly sometimes I refer to as the David Hasselhoff equation. Why? I don't know, because people used to know who David Hasselhoff was. You don't hassle the Hoff, but he hasn't been on whatever show he was on for a decade now. But anyway, Henderson-Hasselbalch equation. This is absolutely equation you are going to use a ton in chapter 17, and you're going to love it. The only tricky part is to remember that you add right here. Okay, that's something that some kids forget. Because we're used to taking the negative log, right? But that's fine. Like we are taking the negative log here and then adding. And then the only other part is to remember it's B over A. And so base over acid, and the base is always the anion, and the acid is always the acid. So when I was younger, I memorized David Hasselhoff was a bad A. And that's just dumb, but it helped me remember that in the Hasselbalch equation, it was B over A. Does that make any sense? Like, it's stupid. Oh. But whatever. Okay, we're going to apply this Huh? Right here? Okay, whatever helps you whatever helps you get it is fine with me. All right. So we can solve these. And these are actually sort of complicated problems, but if we use the Henderson-Hasselbalch, it's going to be easy. So it says, what is the pH of a buffer that is 0.12 molar in lactic acid? So that's easy. There's my acid, right? And 0.1 molar in sodium lactate. Ka for lactic acid is 1.4 times 10 to the negative 4. So we just take this, we say pH equals the negative log of the Ka. Here's the Ka, 1.4 times 10 to the negative 4, and then plus or minus, plus the log, and who's first? Base. All right, so the base must be this number. Okay, and look, sodium lactate does not sound like the name of a base. And it really isn't a base, but we're talking about this common ion that we talked about yesterday. When we introduce this thing, that's the A minus that's making this situation work. So we have 0.1 over 0.12. And you just plug that in, and you're ready to roll. All right, we're going to do like 10 problems. So if you need a calculator, come grab one. These two were just barely charged. There's more back here. I now have 20 loaners. But when you're done, will you please put them up here? Oh, I'm still recording. This is right here. That's a 2. What's that? Absolutely does. And you can do the ice table, but it will give you the exact same thing to within like the 10,000th place. Like depending on how you round, it gives you the exact same thing. Right, where? It's 0.1 molar, yeah. All right, what do we have? 5.44. Okay. So, yeah, that's the pH of this solution. So if I had some weak acid that I added some sodium fluoride to, we would have 5.44. Now, this would be a buffer, by the way, because it would have the weak acid, and we don't care about Na, remember, but it also has excess F minus. Okay, that produces a buffer because the base can react here and the acid can react there, both of which will neutralize. Yeah, and produce water, and this water doesn't affect pH, right? Now, this part is not asked all that often. It's this part. And it's not any worse, you just have to be a little tiny bit better accountant. So now, a buffer's role is to try to mitigate the effects of an acid or a base being added. So if we make a change now, we determine how the neutralization reaction affects the amounts of weak acid and its conjugate base in solution. And then we use the Henderson-Hasselbalch equation to determine the new pH. Okay, so here we go. This is my buffer. All right, if I add hydroxide, all right, then we come up here. If I add H plus, that one, thank you. I draw 20 million arrows a year, so hey, eat it, kids. You guys, well, sorry, it's hard to be me. Okay, now, I know it's hard for everyone to see, but the buffer had a pH of 4.74, and I'm adding straight hydroxide, but it only went to 4.8. The change was very small, even though it should be huge if I'm adding just straight hydroxide. Now, if I add just H plus, it goes to 4.68, which is not that drastic of a change, even though I added just straight H plus. The reason was the buffer. Okay, this thing that looks ugly is super important. And it's not hard, but it's really important. So in the Henderson-Hasselbalch equation, so I have my buffer, and I come along and I add base. If I add base, it's pretty easy to think. The amount of the base goes up, and the amount of the acid goes down. So what we're saying, remember, just real quick, remember this piece of the Henderson-Hasselbalch equation? It's going to change. If, look at the screen for a second, if I come along and I add base, the top number goes up a little bit and the bottom number goes down a little bit, and then I recalculate. It has to do with Lachette, really, yes. Okay, now, I add acid. If I add acid, the amount of acid goes up and the amount of base goes down. Now, I'm going to erase this because that could lead to someone thinking the wrong idea. I'm going to keep B on the top. The base goes down and the acid goes up. It doesn't really matter, but you can see why I would do it that way. Okay. So this is not rocket science. If you add more acid to something, the amount of acid in it goes up and the amount of base will go down. If I add more base, the amount of base goes up and the amount of acid goes down. Okay, you with me? Good. All right, so let's do it. So a buffer solution is formed by adding 0.5 moles of sodium acetate and 0.5 moles of acetic acid to 1 liter. This is given to you a little bit different, but it's the same because the volume's 1. But anytime it gives you just moles, that is a red flag for sure, because all this crap has to be in molarity, right? But that's okay, because I also said it was in 1 liter, so it's 0.5 moles per liter. All right, what is the pH of the solution? Okay, so the first thing to do is to calculate this using the Henderson-Hasselbalch. So here's your acid. It names it. So this must be your what? Base. They're the same number. What's the log of 1? 0. I think. Okay. Don't leave me hanging like that. All right. So if you have the same amount of moles, then the pH is just equal to the negative Ka, or negative log of Ka. Now, you can still plug it in, okay? And we plug that in, and we get 4.74. Anyone else have that? All right. So here we go. Now, I'm going to write this out. It was the negative log, sorry. Uh-oh. Where's my undo? So it's pH equals the negative log of my Ka plus log B over A. Now, we already know this piece right here because it was just the answer. So this piece, mathematically, is 4.74. Plus, okay, now we're here. What would be the pH after the addition of 20 milliliters of 0.2 molar NaOH? Okay, so this we do have to do a little bit of math. Well, I shouldn't put brackets because that's misleading too. we need to find the amount of moles I'm adding here. Okay? We all right with that? So I'm going to take point. Oh, no, I'm still in the eraser tool. Oh, Thomas Davidson. Don't make me say, oh my laws. I'm pushing the freaking button. It tells me to 0.02, all right, times 0.2. You okay with that? And that's 0.004. Correct? Okay. That's how much base I add. You take the volume times the molarity. Okay, now we must be careful. This number is not what goes in your denominator. This is your numerator. This is the change to the base, not the base. So what did I have before of base? 0.5. Looks right here, 0.5. All right. So now my base is 0.5, and then do I add or subtract 0.004? I add. If I add base, base goes up. So I now have 0.504 on the top. It matters, yeah, but not much. All right. There you go. So what do I have in the denominator now? 0.496. We know why? Okay. Because it took 0.004 acid and converted it to 0.004 base. So the base went up 0.04 and the acid went down 0.04. And then we redo our math. So this, you already have this, 4.74 plus whatever this new value is, the negative log of that. What, did you have this number right here, Isaac? What is it? 0.0069. And you ended up with 4.751. Is this very different? No, not really. Not really at all, right? How come it didn't change very much? Because this thing is a buffer. It has the ability to take the OH and bind it to something so that there is a very small change. Okay, now, I want to do something real fast, and you don't have to understand what I'm doing real quick. But this was 1.8 times 10 to the negative fifth. All right? This is equal to my concentration of H plus in this solution. Okay? If you're not with me, don't worry about it. But now, what I would like you to do, we said we had 0.004 OH minus, right? Is that correct? Okay, so if we have 0.004 OH minus, that will neutralize this, right? Are you with me? Okay, so I'm going to take 0.004 and I'm going to subtract. Someone do this for me. 0.12348. Subtract that for me. Okay. Now, what I would like you to do is take the negative log of this number. You get 2.39. Now someone take that and subtract it from 14. Okay. This, my friends, and if this part didn't make sense, don't worry about it. This is what the pH should have gone to. If it was not a buffer, that pH would have gone way up to 11, and we wouldn't even have an acid anymore, right? We would have had excess base, which was this number, in case you're wondering where that came from. And so then this number was the pOH, right? So the change, even though, look, is this very much? No, that is a tiny amount of stuff. But this is an even tinier amount of stuff, right? So comparatively, this is like 2,000 times that. That's not right. 200 times that. Sorry. All right. So it's in acid land. It should have had a major change in pH. But since we had a buffer, we only changed like 0.01, essentially. Buffers are extremely effective at what they do. Go ahead. And hey, anytime you have these, it's from the original. Okay? So this piece is asking you from here. Don't do any of the math here. It's always from the original. So try that. We're now adding acid, which makes acid go up and base go down. All right, so it was 4.74 was the first piece, right? Because that's not going to change. All right, plus log B over A. So I first needed to convert this to moles. Okay, so I have 0.01 times 0.25, so is it 0.0025? Okay, since I added acid, that means the base goes down 0.0025 and the acid goes up 0.0025. So this is 0.5, sorry, I got it. The bottom is 0.5025. This is 0.4975. Okay, I don't know why my brain was so stuck on that one. And you do all that business, and you end up with 4.740. Very end answer. Okay, all of this. 4.75. $4.740? Okay, sorry. I could see her calculator and I thought I heard two different numbers. Okay. Was that really that big of a change? Nope, it was 0.04. I won't do the math on this one, by the way, but it probably should have gone to something like 1.2, 1.3. Like, it should have gotten way more acidic. But it didn't because we're talking about buffer. Okay, here's more. Calculate the pH of a buffer solution made from equal amounts of 0.3 hydrochloric acid and 0.7 molar sodium fluoride. All right. Now, this one, base, and it can accept acid and makes the changes to the pH very small. Okay. Tomorrow, I think I'm going to give you like a little checkpoint quiz. I'll give everyone 100% on it as long as you try it, but I will grade it to see how you're actually doing. Okay. This video will be posted. Read the book. These are tricky, but